Hello everyone, I am Deepak Paliwal. So in this lecture series, we are discussing about deformation mechanisms in the FCC material. So to understand the deformation mechanisms, there are some factors, there are some terminologies we need to understand. So one concept is result shear stress. Today we will discuss in this lecture. So what is the result shear stress? Today we will try to discuss about this topic. So result shear stress. So whenever the plastic deformation starts, or whenever plastic deformation is going to start, there is a need of shear stress. Suppose this is your material and you are deforming this material. For the deformation of this material, we need, suppose the deformation is happening like that, so this is only possible with the help of the shear stresses. So at the micro scale, where the deformation is happening with the help of sleep systems, so I am calling it sleep systems. So sleep systems, which we have already discussed, the combination of the sleep plane and sleep direction. When I say the sleep plane and the sleep direction, that means the sorry, it is not working properly. Let me rub it off again. Closest packed plane and closest packed direction we are talking about. Okay, so at the micron scale, we need the shear stress for the plastic deformation. So the question arises when we apply the tensile load or the unidirectional load. Suppose I am having this type of material and I am applying unidirectional load. So would this unidirectional load or the unidirectional stress will contribute to the shear stress on the arbitrary shear stress on a particular sleep plane? So let us try to understand whether this uniaxial stress is contributing into the shear stress or the shear component on a particular sleep plane. So let me have again let me have this kind of shape or this type of material, and I am applying the sigma load along the y direction. This is my x, this is my y, so I am applying the load along the y direction. Let me have a sleep plane, arbitrary sleep plane, which has the sleep normal and prime. Let me call this area is a prime, this area is a, and let me have some other color to show the sleep direction. So this is our sleep direction, and this is our axis of loading. So let me have some angle, let me draw some angle with the similar color what I have chosen. So this is our theta. Theta is angle between sleep plane normal and loading direction. Okay, again, lambda is the angle between sleep direction and loading direction. Now let me have I can also call the force, unidirectional force is along this direction. Okay, so if I want to write a prime in terms of a, so I can take the projection of a prime over a, and from the simple geometry we can calculate a prime is equal to a cos theta. Okay, in a similar fashion, I want to take the component of this force along the sleep direction. of F along slip direction. So how we can do that? Let us call along this direction we have F prime. F prime is our shear shear force. Okay, so shear force is equal to F cross cos lambda. Okay, and this I am calling this is equation 1, this is equation 2. Now I want to calculate the shear stress, which is our resolved shear stress. So I am dividing both sides with the A prime. Okay, F divided by A prime cross cos lambda. Again, F prime, by the definition, by the simple definition, the shear force divided by shear area is equal to, this is your shear stress. Again, from equation 1 we can write A prime is A cos theta, A, and again I will write cos lambda and cos theta. So this F by A, let me choose some color here. This is your the unidirectional stress what you are applying, and this cos lambda dot cos theta is your Schmidt factor. It is Schmidt's factor, and this is your resolved shear stress. So when the plastic deformation happens, when sigma becomes sigma y is yield stress. So when the material reaches to its yield stress, then the plastic deformation is going to start. So when sigma reaches to sigma y, tau reaches to a critical resolved shear stress value. Tau becomes its critical resolved shear stress value, and it is possible, this is the again cos lambda and cos theta, which is our Schmidt's factor. So the when this sigma becomes to sigma y, the tau becomes to the critical resolved shear stress. So here, for a particular slip plane, a particular value of critical resolved shear stress is required. When our shear stress is greater than CRSS, that is critical resolved shear stress, only then the plastic deformation on that particular plane will going to start. Let us find the effect of the various plane with respect to the loading direction, or rather I would say the effect of loading direction on a particular plane on the critical resolved shear stress. So here we have equation tau sigma cos lambda cos theta. For a particular case, let me have a plane which is along loading direction. Plane along loading direction. If I am saying like this, that means the theta is equal to 90 degree. Plane normal making angle 90 degree with loading direction. So we can visualize it like this. This is my material, this is my loading direction, and I am making a plane, or assuming, rather I should say, assuming a plane. If let me have different color. Okay, so I am assuming a plane like this. So this is my normal, and it is making angle 90 degree. That means theta becomes 90 degree. If I put this value into this equation, we know cos 90 degree is equal to 0. So tau becomes 0, means critical resolved shear stress for this particular plane becomes 0. So applying the sigma stress, giving 0 critical resolved giving 0 resolved shear stress, that means the deformation on that particular slip system would not happen. Again, I am taking another example. in which I am taking a plane perpendicular to the loading direction. So here we have this our material in which we are applying sigma, and this is again I am taking with the green color for the better understanding. Okay, so this is the plane. So our normal and loading direction having angle is equal to 0 degree. So now let's see, again put into the equation is 0 degree and becomes the 90 degree lambda becomes the 90 degree with the loading direction. So suppose any arbitrary direction I am assuming, slip direction, so all the direction lying in this plane becomes the 90 degree to the loading direction. So again if I put tau sigma cos theta cos lambda, again tau becomes 0. That means the result shear stress by application of this stress becomes 0. That means again the slip will not happen, or deformation on this particular plane or this slip system will not get activated by the application of this sigma. So in this lecture we have learned about the result shear stress, what is the result shear stress, and how we can resolve a particular stress on an arbitrary plane. So the final equation we have reached is tau equal to sigma cos theta cos lambda, and when this sigma reaches to sigma y, this tau becomes tau CRSS. That means for the plastic deformation, which is defined by the sigma y, means whenever the stress reaches to the sigma y or greater than the sigma y, the plastic deformation is happening. So for the plastic deformation on a particular slip system or a particular plane, the critical result shear stress value must be exceeded, like the tau value by having the sigma or any kind of stress, this tau value should be greater than the tau CRSS, then only the plastic deformation will happen. Okay, in the next lecture we will talk about the Schmidt factor or the Schmidt law in detail. Till then, bye bye, thank you for watching.